Oh, got to do my favorite student. Michael, even though it's your birthday, who is my real favorite student? Good old Anne. It would be very ironic if someday I actually had a student named Anne Serkey. That would be confusing. Energy is the ability to do what? This is helpful in your understanding, so you want to know this. Bree, what? Work. 1 mark. Number 2, what is the minimum amount of work it would take for a 55-kilogram student to climb a 6-meter high flight of stairs? Okay, climbing, that means we're doing work against gravity. I can think of it 2 ways. I can either think of it as force times distance, where the force is the force of gravity, or I can actually think of it as a change in potential energy, because for both of them, I'm going to get mgh. Well, the bottom one, I would get final minus initial, but since I'm starting on the ground, what's my initial potential energy? 0, and I still get mgh. Mass, hopefully they gave it to me, 55, 9.8 times 6. Double check, is the height in the same direction as the force? So make sure if I ever give you a picture, don't use the slanty diagonal length of the stairs for the work against gravity. You would use, if it was a ramp, the slanty length for friction, because friction acts along the ramp, absolutely, but you wouldn't use it for gravitational force, for gravitational work. It's going to be 55 times 9.8 times 6. 3,234. 3.23 times 10 to the 3rd joules. A 2-kilogram ball is 5 meters above the ground, and it's falling at 5 meters a second. What's its total energy? How do you think, I haven't really done this, how do you think I'd find total energy? What do you think total energy would be? Kinetic. Instead of and, can you use a mathematical word that means the same as and? Plus. How about TE is my new abbreviation for total energy? Equals KE plus PE. It's going to be a half mv squared plus mgh. The total energy is going to be 0.5 2 5 squared plus 5 9.8 times 5. Can I do this in my head? Because half and 2 cancel each other out. Hey, maybe I can do this in my head. It's going to be 25 plus 25 times 9.8. 25 times 9.8 is going to be 25 times 10, 250 minus 245 and 20. Is the answer 270? No, I'm way off, Mr. Dueck. 25 times, oh, good gosh. Boy, did I botch that. 5 squared plus 5 times 9.8 times 5. Where was I way off? 270, I was right. Am I right, or did I type something in wrong here? Mass, 5 squared, 5m. Oh, Mr. Dueck, you put a 5-kilogram mass. Jeez. At least my math was right when I did it in my head. I did say 270. How about that's supposed to be a oh, that makes it easier because now it's 98 and 25. I can do that in my head too. It's going to be 125 take away 223. Is that right? A little worried. I got to keep this sharp. I'm in my 40s now. Got to use the calculator less and keep my brain going. Hey, I bet you I'm going to be using some kind of a definition of work as the area underneath the graph in this question. Do you know how I know without even reading the question? Because there is a... Now remember, not only is the area under the graph work, that also means it's the change in potential plus the change in kinetic, because it also means it's the force times distance. So I can actually use that area to figure out other stuff. Let's see. Using the following graph of force versus position, find the total work done moving from 0 to 5. 5 is right there. I guess the total work done is this area. I think I would divide it into area 1 and area 2, where area 1 is a triangle. Its base, 3, times height, 200, divided by 2. 200 divided by 2 is 100. You know what? Area 1 is 300 joules, which means C is wrong because I know I'm doing more work than that. Area 2 is length times, Dueck, length times width. It's going to be length 2 times width 200. Area 2 is 400, which means that's wrong. I guess the answer is it B? Yes? Did I give you a second part in reference to? Okay, oh, I did. Ha! I was going to say this would have been a great chance to give you a follow-up question. I was worried that I had not. If the graph in question number 4 represents the work done on a 4-kilogram mass, find the speed of the mass when it reaches 5 meters. The mass is initially at rest. So now I can say this. What is the area under a force versus distance graph, by the way? Work equals, I can say work equals work. By the way, I wouldn't actually write that out, but just so that you know my chain of reasoning, what I'm really going to be then saying is this. 700, the work done, equals, you know what? I don't think we're talking about going uphill at all, so I think I can do that. It's going to be the change in kinetic, which is going to be a half mv final squared minus a half mv initial squared. Wait, Mr. Dueck, you can do that too. Why can I do that too? Because it did say this object, Petra, started at what? Rest, right? So initial is 0. By the way, if you haven't picked up on it, I like 4 and 5. I like 4 and 5. I like 4 and 5. 4 and 5 is a nice question. Giving you a graph and then asking you to do something with that graph, either as a force times distance, because I also could have said the area equals force times distance, which means I guess I could have asked you to find the average force, or as a change in potential, change in kinetic. That's because otherwise finding the area under the graph, that's a little wishy-washy, too easy. But combining that with this, hey, I like that. Whoa, what are we trying to find? Oh, speed. So I guess the speed, final speed is going to be 2 times 700 divided by the mass, and then square root to get the v by itself. It's going to be the square root of 2 times 700 over 4. Well, 2 divided by 4, that's the same as 1 over 2. This is really 700 divided by 2. It's the square root of 350. Not very nice. 2 times, how about turning the calculator on, Mr. Dueck? 2 times 700 divided by 4. It is the square root of 350, isn't it? Yes, it is. Double checking. 18.7? There you go. Yes? What if you got the force wrong? There is no force. Okay, so what you're really saying, Mr. Dueck, what if I got number 4 wrong? Yeah. You got number 5 wrong. It's a quiz. It hardly affects your mark at all, and I know that'll tick you off so much that I guarantee that means you're going to be so angry when you write the test, you'll probably get this right. Yeah? Tell me how you found the acceleration.
I did work equals force times distance.
Okay, that will work because actually work equals average force times distance. If it's a changing force, it is a look up, look up, look up. It is a changing force. You know how I know? Because it gets bigger at the beginning. If you just went, oh, the force is 200, which is what a lot of kids want to do. No, it's 200 at the end. But it wasn't 200 the whole time. So if you found the force using work, that's acceptable, although, no pun intended, more work than what I just did, I think, yes? Oh, heck, that pun was totally intended. I'll take that. That was a good one. And more work on work. But if every year I'll see kids, for example, and I'll even give you a hint. You're going to see this graph, a similar something like this on your test. I'll see kids say, oh, the force is 200. And they'll use that, and I'm going to give them a 0 for a big chunk of it. Force is not 200. Look at the graph. It ends up being 200. And if that's what you did wrong, then I'm really drumming it. It ends up being 200. But look, it starts out at 0. And it gets bigger for a while. And then it levels off for a while. In fact, the average force, what did you get for the average force, Nate? It would have been, yeah, which is kind of hovering in midair. Because the other thing is, a lot of kids will say, well, isn't the average force, if the final force is 200, isn't the average 100? No, because you weren't increasing the whole time. This is yeah. So yeah, that works. I'll take that. Humbly, I suggest mine like better and cleverer. Hey, let's do an escalator. Escalator's great example of machines that do work against gravity. And we're assuming that you move at a steady speed. It is true, Jordan, I had a kid last year challenge me. Mr. Dueck, actually, I start out at a speed of 0. It's the escalator that increases my kinetic energy a tiny bit. You know what? We're ignoring that. Because once it gets you there, actually, you sort of step onto the escalator at the same speed as it's moving. You supply the change in kinetic energy. It really depends, I guess, how you get on escalators, William. And okay, fair. We're in our magic idealized escalator. It's used to move 20 passengers a minute to the second floor, which is 5 meters above the first. Assuming the average passenger is 60 kilograms, what approximate power? Oh, power. Well, power is work over time. Power is work over time. What was the other definition of power? The one that came out of this when we wrote out work was force times distance. We did also say, this is not on your formula sheet, it's force times speed, because distance over time was speed. But did they give me a time race in this question? Do I see them talking about, do I see them, they did give me a time. Begins with letter M and rhymes with in it.
Seconds.
They gave me a time, a minute, which, how many seconds actually then? 60. There is a time in here. I'm going to use work over time. And the time that we're talking about is 60 seconds. The work is going to be mg, and use the 5, not the 10. I guarantee one of the answers that you could pick from would be if you used the 10, because that's the direction the escalator is traveling. Yeah, but that's not the direction of the force that we're doing work against, right? So it's going to be over 60. There's going to be a 10 here. There's going to be a 9.8. Hey, what's the total mass? How much is the mass of one person? Hello? 60 times. How many people do we move in a minute? I think the total mass we're moving is that. You could also instead, Nate, have converted this into 1 second. You could have said, well, I'll divide the 60 minutes by 1 second, and I'll divide the number of people by 60. But anyways, this works as well. In fact, quite conveniently, this 60 cancels with that 60. This is really 20 times 10 times 9.8. This is really 20 times 98, which is going to be 1,960.
Why do we use 10?
Oh, good gosh, Mr. Dueck. After I told you not to use the 10, I used the 10. Cliff, why do we use 10? Because I'm tired. Because I had a brain cramp. Much like someone else on the quiz. You're not alone, my friend. So, you know what? The 60 cancels. It's going to be 20 times 5, which is 100 times 9.8. I think it's going to be 980 power. What? Oh, you know what? 1,000 watts, I guess, is the closest answer here, yes? So you would have to have, for this escalator to run, the electric motor would have to be at least a 1,000-watt motor. Okay? What would happen if more people got on than 20 in 1 minute? The escalator would slow down. And you can actually overload an escalator. If like all 30 of you went on the same, probably could handle 30, because I think they set it up so that every stair can be full with one person. But if you ask it to do more, the motor will slow down. And the problem is, because they're electric motors, when electric motors slow down, they start to overheat. You'd have other issues. How much work is required to stop a 1,200 kilogram car moving at 10 kilometers per hour? Well, wait a minute. Mr. Dueck, I don't see a force, I don't see a distance. That was a dumb definition of work to write down. Well, it's also the area. Wait a minute, Mr. Dueck. I don't see no graph. That's a dumb definition to write down. Our third definition of work, which we call the work energy theorem, is that. And they're not mentioning any kind of a change in height. So, Manish, I'm going to assume the change in potential is 0. This is going to end up being KE final minus KE initial. And the final is 0. Work is going to be... Now, I'm already sensing I'm going to get a negative answer. Although it looks like they just wanted the magnitude, because I don't see any negative answers kicking around. So I'm just going to get the magnitude. Going to be 0 minus a half mv initial squared. It's going to be 0 minus 0.5 times 1,200 times 10 divided by 3.6. I bet you thought, Jordan, that I'd missed that it was in kilometers per hour. It's not. But I was so lazy, I said, why don't I just do the conversion squared right in the question? Because kilometers per hour is divided by 3.6. I remember that from Physics 11. So it's going to be a half m 10 divided by 3.6. How about 36, Mr. Dueck? Try that again. 3.6 squared. Is the answer 4,630? Joules. Oh, yoink. 4.6 kilojoules if they wanted to go into kilojoules. Turn the page. What have we got? A couple more multiple choice and then a good written. Excellent. Use the following information for number 8 and number 9. Tarzan, 75 kilograms, swings from his vine from a height of 2.5 meters above the ground. At the end of his swing, he's only 2.4 meters above the ground. This is a much more realistic question. If you've ever been on a rope swing, you never quite get back to the same height as you originally started, because in real life there is friction and air resistance. You lose some energy. Also, you can often hear the rope creaking, for that matter. You hear some sound. How much work has been done by friction? What is the work done by friction? What do we call that? Begins with the letter H. Heat. Okay. Alex, is there a change in height? Yeah. Is there a change in speed? Yes. Is there a curvy, yucky path? You know what this is a job for? Conservation of energy. G. Right? I'm going to go, okay. KE initial plus PE initial equals KE final plus PE final. And they're talking about heat, so I'll include heat. Are any of these 0? I think when you start out on a rope swing, you're standing still and then you lift your legs up and jump. Oh, and I think at the top of the rope swing on the other side, you're also briefly standing still, so you lift your legs up and jump. Howdy, howdy. Pause. Anything else 0? You might be tempted to say potential energy is 0. It's 0 at the bottom, but we're not talking about no bottom in this question. We're talking about the top, and then the other top not quite so high. So I guess the heat, which I'll do in red now since that seems appropriate for heat, is going to be initial minus final. Not dividing by final to move it over. Minusing. I think it's going to be mgh initial minus mgh final. Okay. Hey, does the heat, does the mass cancel here? No mass in heat, so no. Heat is going to be, what was Tarzan, 75? 75 times 9.8 times 2.5 minus 75 times 9.8 times 2.4. Can I do this in my head? You know what? If I was going to do this in my head, I'd factor out the 75 and I'd factor out the 9.8 and I'd say I have a 2.5 minus 2.4, which is a 0.1, times 9.8, which is almost 1. It's going to be really close to 75. The answer is A, yeah? Yeah, I did that one in my head too. But I factored the first two numbers out and then it got easier. If there were no friction. Now we're in our magic physics world, William. What would Tarzan's velocity? Cross out the word velocity. I should fix that. It's a speed. You know how I know it's a speed? Because work and energy are what? Scalars. Scalars, right? I'll fix that. Okay. Alex, is there a change in height? Is there a change in speed? Is there a curvy path? You know what? This is a job for conservation of energy. And they're telling me this time, ignore heat. Are any of these 0? At the top? At the bottom? It's going to be mgh initial equals a half mv final squared. If we ignore heat, that happens. V final, I think, is going to be 2 times g times my initial height square rooted. Two times 9.8. Try that again. Times my initial height. Oh, square root of that is 7 even. D. And the written. A roller coaster car of mass 1,000 kilograms, traveling with an initial velocity of 4 meters per second. Okay, kinetic energy initial, not 0. Is 18 meters above the ground. It drops to the ground, then climbs a 10-meter high hill. How fast is it traveling at the bottom? How fast is it traveling at the top of the second hill? Hey, Bree, is there a change in height? Is there a change in speed? Is there a yucky, curvy path? I think this is a job for conservation of energy. I don't think it's talking about heat or friction or anything, so it's going to be KE initial plus PE initial equals KE final plus PE final. No heat. And I think at the bottom I can do that, but I don't think I can cancel anything. Nothing else is 0. So this is going to be a half mv initial squared plus mgh initial equals a half mv final squared. Michael, you know what we're going to do for your birthday? We're going to get rid of mass. Happy birthday. I'm going to do one more thing. To get rid of fractions, I'm going to go times by 2, times by 2, times by 2, because that clears that fraction, that clears that fraction. Yeah, it gives me a 2 in front of the GH, but I'll take a single 2 over a pair of halves any day. And I get this. VF squared equals VI squared plus 2GH. Looking very similar, by the way, to VF squared equals VI squared plus 2AD, because that's really where it comes from. And William, how do I get rid of a squared, my friend? I think I agree with you. So this is going to be the square root of 4 squared plus 2 times 9.8 times 18. Okay, Mr. Dueck, let's see you do this one in your head. Okay, maybe. 2 times 18 is 36 times 9.8. 36 times 10 is 360. 36 times 9.8 is going to be 360. Take away 3.6. Take away 3.6. 360 take away 7.2. 360 take away 7.2 is going to be 352.8 plus 16 is going to be 362.8. 368.8. Square root of that. Ugh. I got to go to a calculator. I was kind of hoping it might work out nice. At least I got the 368.8. 19.2 meters per second. Now, if you got that, you get 3 out of 3. Otherwise, I would probably do something like this. I would give you 1 mark if I saw that, 1 mark if I saw that, half mark for the numbers, and a half mark for the answer. Probably something like that. How fast is it traveling at the top of the second hill? Kinetic initial, potential initial, kinetic final, potential final. Ugh. None of these are 0. It's going to be KE initial plus PE initial minus PE final. That equals KE final because they want the final speed. It's going to be a half mv initial squared plus mg h initial minus mg h final equals a half mv final squared. Hey, Michael, do you want mass for your birthday? No, of course you don't. Oh, and Mr. Dueck, could you go times by 2, times by 2, times by 2, times by 2? I could. You don't have to. Again, you can replace the halves with 0.5s and carry them through. But, Sammy, I like to clear fractions. That's my birthday present. I'm running out of room here, Mr. Dueck. Looks like it's going to be come on, there we go. VI squared plus 2GHI minus 2GHF equals VF squared. You know what? Square root. Final speed is going to be VI was 4 squared plus 2 times 9.8 times, I think, 18 minus 2 times 9.8 times 10. Please work, Mr. Dueck. Hey, you know what? I'm going to get really clever. I'm going to go second function enter a couple of times, and I'm going to bring that line because that's the 4 squared plus 2 times 9.8 times 18 minus 2 times 9.8 times 10. Wasn't that clever, huh? Okay. Square root of this. 13.1? Yeah, people nodding? 13.1 meters per second. That one, for some reason, was out of 4. You know what? I'd probably go like 1 mark for that. I'd probably go 1 mark if I saw that, 1 mark for the numbers, and how about 1 mark for the answer, or something like that, I don't know. But if you get the right answer, again, William, 3 out of 3, as long as you showed some work. Can you give yourself a nice big score out of, count 'em, 16, please?